Welcome to Study Loop.
For this problem, we're analyzing the angular momentum of the Sun-Jupiter system. For the first part, we're going to find the total angular momentum. In order to do that, we're going to use equation number 30 that was given in the textbook, which states that the total angular momentum, L, is equal to the reduced mass, mu, multiplied by the square root of gravitational constant, g, times total mass, m, times the semi-major axis, A, multiplied by 1 minus the eccentricity, E, squared. Now, several of those numbers were given in the problem. Those are listed up in the upper left-hand corner here. We have that the semi-major axis A is 5.2 astronomical units, the eccentricity is 0.048, and the period, which we'll need later in the problem, is 11.86 years. In order to solve the problem, we're also going to need a few other constants, including the mass of Jupiter, the mass of Sun, and the gravitational constant, g. So I've listed those in the upper left as well, mj, ms, and g. So let's take the formula and break it down so that we can figure out where we need to plug our numbers in. So angular momentum, that's what we're looking for. The reduced mass is equivalent to the product of the two masses, mass of Jupiter multiplied by mass of the Sun, divided by the sum of the two masses, mass of Jupiter plus mass of Sun, times the square root of gravitational constant. Again, that capital M is the total mass, mass of Jupiter plus mass of Sun, times A, times 1 minus the eccentricity squared. This is basically just a big stick it in your calculator type of a situation, plug and chug here. And once you do so, you get an answer of, oh, wait a minute, before we plug things in, we have to make sure that everything is in the correct unit. So let me actually back this up just a moment. Because if you notice, my semi-major axis was given in AU. However, AU is not the unit of distance that we want to be using, because if you look at the units for G, the gravitational constant, that's newtons times meters squared per kilogram squared. So every other number we use has to be in that same set of SI units. So we're going to have to actually convert. So the A, which is currently 5.2 AUs, in order to convert that into meters, we need to know that 1 AU is equivalent to 1.496 times 10 to the 11th meters. 1.496, I need to give myself more room, times 10 to the 11th meters. So that's going to be part of our calculation as well. When we plug in A, we're not going to plug in 5.2. We're going to plug in 5.2 times 1.496 times 10 to the 11th in there. Our masses are already in kilograms, so we're good. Gravitational constant is good. The eccentricity doesn't have a unit, so the rest of those are good. Now we're ready to plug this all into our formula. And when we do so, we get 1.9255 times 10 to the 43. 1.9255 times 10 to the 43. That's quite a lot. Kilogram meters squared per second. So that's for part A. So here was our answer from part A, the total angular momentum of the Sun-Jupiter system. Part B, we're going to look for just how much did the Sun contribute to that total angular momentum. Angular momentum is R cross mv, where R is the position of the object in question relative to the focus point, m is the mass of the object, and v is the velocity. To find the location of the Sun relative to the center of mass of the system, we're going to use equation number 20 from the textbook, which says that the position relative to the center mass, R1 of object number 1, is equal to the mass of the other object, M2, divided by the sum of the masses, M1 plus M2, multiplied by the distance between the two objects, represented as R12. So to solve this for the sun, we're talking now about the position r of the sun. I'm going to use this circle with a dot in the middle to represent sun, is equal to the mass of the other object, which is Jupiter, so mass of Jupiter, divided by the sum of the masses, mass of the sun plus mass of Jupiter, times the distance between the sun and Jupiter. Now we're assuming a circular orbit, it says in this problem, which would mean that the distance is constant all the way around because the radius is constant. So the semi-major axis A is a pretty good approximation of the distance between the sun and Jupiter. So that 5.2 astronomical units, that's what we'll use for R12, the distance between sun and Jupiter. So we go ahead and we plug those numbers in. We have the masses that were given over here and the astronomical units for A, the semi-major axis. And we plug all of that in. We get that this distance of the sun away from the focus is pretty small, 4.957 times 10 to the negative third AU, which makes sense because the sun doesn't move a whole lot in circles due to Jupiter's orbit. Okay, so we have the R. M is just the mass of the sun when we're looking back at R cross MV. The next thing we have to think about is V, the velocity of the sun. Well, again, we're assuming that eccentricity is 0 in this part of the problem, meaning that we have a perfectly circular orbit, and we're going to also assume a constant speed. So therefore, the velocity can be calculated by the distance divided by time. The distance around the orbit is going to be 2 pi r, the circumference of the orbit. We'll use that r that we just calculated down there, divided by the time it takes to go once around the orbit, which is the period, p. We have to be careful with these. We have to make sure that we're, again, using the right units. So that r that's currently in astronomical units, when we actually plug it in, we'll be plugging in with the unit conversion. So it'll be 4.957 times 10 to the negative 3, that number, times the unit conversion into meters, 1.496 times 10 to the 11th, that's meters per AU. So we end up with units of meters on our radius, which is what we want. Similarly, we're going to have to do a unit conversion for the period. So the period it gave was 11.86 years, but we need it in seconds. So to do that conversion, it's going to be 11.86 years times, we can actually look up the unit conversion in the appendix, that 1 year is equivalent to 3.156 times 10 to the 7th seconds. So we're going to have to include that when we do the period calculation. So years times 3.156 times 10 to the 7th. That's how many seconds are in a year. So years cancel. And that's how we calculate the period in seconds. So all of that is going to be what we'll plug in for P. So again, plugging in the numbers and just doing a big calculator situation. What we're going to be plugging in, we can actually go back to our angular momentum. We're ready for that at this point. Will be, well, R cross V, knowing that we have a circle, the velocity will always be tangential to the circle, whereas the radius will be perpendicular to that velocity, to that tangent. So for example, if I draw the circle and say the object's over here, the object's moving this way, that's the direction of the velocity. This is the direction of the radius. Because those are perpendicular, R cross MV is equal to just R times M times V. So we can just multiply the radius of the sun's orbit, which is right there, multiplied by the mass of the sun, which we have over here, multiplied by the velocity, or average velocity, which will be given by this equation with all the appropriate unit conversions. And then we can just go ahead and plug those numbers in, and we get This answer right here, 1.837 times 10 to the 40th kilogram meters squared per second. And that is the sun's contribution to the angular momentum. For part C, it's going to be really, really similar to part B. We're just going to be swapping out the numbers for the sun and the numbers for Jupiter. Everything else is exactly the same. So this is for Jupiter. So we'll be doing the same thing for calculating the distance for Jupiter from the center of mass. Again, just swapping out the subscripts. So now since we're looking for Jupiter's position R, it'll be mass of the sun divided by the sum of the mass of the sun and mass of Jupiter. We can still use A, the semi-major axis, as an estimation for the average distance between the sun and Jupiter. And then that will give us a new distance of 5.195 AUs. That makes a heck of a lot of sense that the Jupiter orbital radius is much larger than the solar orbital radius. Jupiter's the one spinning around a lot on its orbit, whereas the sun barely moves. So we take that new radius, and again, we make sure that we do a nice job of checking our units here, including that factor to convert it into meters before we do any calculations. We can use this same formula, 2 pi r over the period, but of course, now we're using the new radius of Jupiter instead of the radius of the sun. The period is the same for both, so we can still use that 11.86 years multiplied by the conversion factor to get it into seconds. And once again, we plug it all into our calculator to get our answer for part C, which is right here, 1.924 times 10 to the 43 kilogram times meter squared per second is Jupiter's contribution to the total angular momentum of the Sun-Jupiter system. Next, for part D, we're going to calculate the rotational angular momentum of each of the two bodies. We are given in the textbook the formulas that rotational angular momentum L is equal to the moment of inertia I multiplied by the angular frequency omega. L equals I omega. So for these objects, which we're going to approximate as spherically symmetric, the formula for the moment of inertia is 2/5 m times r squared, where m is still the mass of the body, and then the r, we are now redefining. R is no longer the position relative to the focus of the orbit. Now r is the radius of the sphere. We're given those numbers. The radius of the sun is 6.96 times 10 to the 8th meters. The radius of the Jupiter is 6.9 times 10 to the 7th meters. In order to calculate this, let's start by calculating the angular momentum of the sun equals. So the moment of inertia, I, is going to be 2/5 times the mass of the sun, same number we've been using throughout the problem, multiplied by that radius of the sun that we were given, squared, times omega. To calculate omega, it's in units of radians per second. So in one full rotation, there's going to be 2 pi radians. And then that one full rotation takes a time measured by the period. The period of the sun is given in units of days, 26 days. So in order to plug that in, we need to convert it into seconds. So we'll take the 26 days times 24 hours per day times 3,600, aka 60 squared, seconds per hour. So our days cancel, our hours cancel, and that's what we're going to plug in. 26 times 24 times 3,600. That's how many seconds are in the period of rotation. I'm just going to put P, period of the sun. Okay, so we plug that all into our handy dandy calculator, and we get that the angular momentum of the sun is given right down here after we plug it in our calculator, 1.078 times 10 to the 42 kilogram meters squared per second. Quite a bit of rotational angular momentum for the sun. For the Jupiter, we're going to do exactly the same thing, just replace all of these subscript suns with subscript j's. And once again, we're going to have to do a unit conversion for the period. So we'll do that in just a moment here. Right, angular momentum of Jupiter is 2/5 times the mass of Jupiter times that radius of Jupiter given in the problem times 2 pi over the period of Jupiter, where the period is going to be 10 hours times 3,600 seconds per hour. That's what we're going to plug in for the period. And we get that the rotational angular momentum of Jupiter is 6.309 times 10 to the 38th kilogram meter squared per second. Finally, the last part of the problem just asks us to compare which contribution or which element contributes the most to the total angular momentum of the system. So just looking at these numbers that we have that we've calculated so far in the problem, we know that the total is 10 to the 43, and the only other exponent that comes close is Jupiter's contribution. So Jupiter moving in circles or really ellipses around its orbit is the biggest contribution to the total angular momentum of the system. In second place is the rotational angular momentum of the sun.